today we're going to continue talking about antiderivatives and integration, but we're going to put a little context around what will be computed. So today we're going to go back and talk more about particle motion, which is really the relationship between position, velocity, and acceleration. And this is something that most of us kind of struggled with last semester, I think, a little bit. And last semester, we, after learning how to differentiate, we discovered the relationship between position, velocity, and acceleration. And that is that velocity, maybe I'll write that up here, is the derivative of position. So if I'm calling the position function p, although it may go by some other name, sometimes it's called x, sometimes it's called s, sometimes it's just called something else. Yeah, d for distance sometimes. Anyway, I'm going to call it p just for now. It's position. Position starts with a p. But the derivative of the position function is velocity. And we learned how to differentiate, so we could find the velocity given position. But what we can do now is, given the velocity, find the position. Okay, because if velocity is the derivative of the position, then that means the position must be the integral or the antiderivative of the velocity. Okay. Now, we can also throw in acceleration here too. Okay. So, acceleration is the derivative of velocity. Which also happens to be the second derivative of position. I guess we're going to throw that in there. Okay, but I'll just erase that just to clean this up a little bit. We can, now that we know a little something about how to find antiderivatives, we can also say that the velocity is the antiderivative of acceleration. So now, instead of just being able to go from position to velocity to acceleration, now we can go from acceleration back to velocity and back to position. So not all of these questions that we're going to look at today have to do with integration. Some of them are just a little bit more advanced particle motion problems, but we're going to go through a few here, and occasionally we'll have to refer back to those integrals and derivatives and whatnot. So number one says a particle moves along the x-axis so that time, so any positive or zero time is its velocity. So that I've got to fix the grammar here. So that at time t, its velocity is given by this function right here. So that's the velocity function. The first part A, is asking for the speed of the particle at time equals 2. Now, does anyone remember what the relationship between speed and velocity is? So the derivative of position is velocity. Speed is very closely related to velocity. It's also describing like how fast you're moving, but also in velocity has this other component which describes in which direction you're moving. So velocity is what we call a vector because it has this directional component to it, and speed is just a scalar. It's just the number itself. So with velocity, you can say like, oh, I'm going 30 miles per hour east versus 30 miles per hour west, and I can note the difference between the direction there with a negative sign. Whereas speed is just, you're going this fast no matter what direction you're going. So the way that we compute the difference between speed and velocity is that speed is the absolute value of velocity. So whichever direction you're going for velocity, the speed, whether it's to the left or to the right, will be the same. So I'll just make a little note here that speed is the absolute value of velocity. So speed is always positive. So at time equals 2, what we're going to do is we're going to find the velocity and then take the absolute value of whatever we get there. So the speed will be the, well, here, I'll just write it kind of using function notation here. The speed at t equals 2 is going to be the absolute value of that function right above, but I'm going to substitute in 2. So negative 3 times 2 squared plus 2 times 2 plus 1. And at this point, we're just going to be doing the arithmetic. So the absolute value of negative 3 times 4 would be negative 12, plus 4 plus 1 would be the absolute value of negative 12 plus 5 would be negative 7. And the absolute value of negative 7 is 7. Now, it doesn't look like this problem gives you any units, so we're just going to leave it 7. On the AP test, you don't want to throw it. You might be tempted to like call it meters per second or something like that. But unless they actually give you units, don't make up units to go along with it. Velocity generally, or speed, is a distance over time. So often it's like miles per hour, meters per second, or something like that. But we don't want to just make up a unit. I don't think it gave us a unit, did it? No. All right, so any questions about speed? It's just the absolute value of velocity. Now, whether or not the velocity is positive or negative will tell you which direction the particle is moving. If the velocity is positive, it's moving to the right, and if it's negative, it's moving to the left. So for part B, it's saying at time equals 3, which direction is it moving? If it's going to the left, then that means the velocity is negative, but it's going to the right, the velocity is positive. So if we calculate the velocity at t equals 3 and see if it's positive or negative, we can say which direction it's going. So the velocity at 3 is negative 3 times 3 squared plus 2 times 3 plus 1. Scroll up a little bit here. So this will be negative 3 times 9, thank you, negative 27, plus 6 plus 1, so negative 20. And it's probably meters per second or something like that, but I'm not going to throw on units. But the fact that the velocity is negative tells us which direction the object is moving. So which direction is the object moving? To the left. Okay, so our answer is going to, we want to say it something like this. So at time equals 3, the particle is moving to the left. Okay, that's our answer, to the left. Because, and this is the justification, the velocity at time 3 is less than 0, or is negative. So the justification is really this little statement right here. And just like last semester, not every time, but most of the time, your justification is just going to be whether or not something's positive, negative, or 0. Like at least half the time, that's what your justification should look like. Okay, part C says if the particle is moving at, or if the particle is at position x equals 7 at time equals 2, okay, what is the position at time equals 3? So here we have to find the position. This is where finding an antiderivative comes in, because we know, and maybe I'll rewrite the velocity function here, negative 3t squared plus 2t plus 1. We want to find the position. So you do want to make some kind of statement about the relationship between position and velocity here. So I'm going to say that the position function is equal to the integral of negative 3t squared plus 2t plus 1 dt. So we need to integrate that. You know what? I should have said that the position is the integral of velocity. Yeah. Really want to make that connection. Make sure, I mean, I think that's pretty obvious what I'm saying there, but just to be very clear about where that's coming from. Okay, so let's go ahead and integrate. We're going to use that power rule to do this. So we've got negative 3 times t cubed, and 1/3 times negative 3 is just negative 1. So it's going to be minus t cubed. Okay, plus t squared times a half, so 2 times a half is 1, so that's just going to be t squared. Plus t. And then plus c. So here is my position function. But we want to know what's the position at time equals 3. The only problem is we don't know what c is yet. So we have to go back and use the fact that at x equals 7, t equals 2 to figure out what that c is. Okay, so x is 7 when time is 2. So I'm going to substitute in 7 for x and 2 for t. And I'll use that to find c. So let's see, 2 cubed is 8. So we have negative 8 plus 2 squared is 4 plus 2 plus c. All right, just trying to isolate c here. So let's see, negative 8 plus 4, that'd be negative 4 plus 2 is negative 2. So, oh wait, how did that 7 become negative? I'm not sure how that happened. So we have 7 plus 2 would be 9. So c is 9. And now we could take that and substitute that back in here. So x of t, or my position at time t, is negative t cubed plus t squared plus t plus 9. And now I can find the position at any time. Okay, just take whatever time you're interested in and substitute that into t. You can compute your position. So in this problem, we want to look at time equals 3. So you want x of 3, or the position at time equals 3. That'll equal negative 3 cubed plus 3 squared plus 3 plus 9. So let's see here. X of 3 is negative 3 plus 9 plus 3 plus 9. So our answer here, the position of the particle at time equals 3 is, let's see here, we've got negative 3 cubed. Oh, I forgot the cubed on there, didn't I? So that's actually not going to be negative 3. It's going to be negative 27. So negative 27 plus, let's see, 18 would be negative 9 plus 3. I think that's negative 6. Does that seem right to you guys? Yeah. So it's 6 units to the left of 0. Any questions about this one? All right. Let's try one that's a little trickier here. It says a particle moves along the x-axis so that at time t is greater than, so for positive t values, its position is given by this position function. So we're calling the position function x. Determine if the particle is speeding up or slowing down. So what does it mean for a particle to be speeding up? Sometimes it has a positive acceleration. Sometimes the acceleration is negative, though. So let me explain what I mean by that. The acceleration is the second derivative of position, right? So if you're looking at a graph of position, the acceleration, whether it's positive or negative, is notated by the concavity of that curve. If it's concave up, you'll have a positive acceleration. Concave down, a negative acceleration. But consider a curve that looks like this. Okay, if I have a positive acceleration, that means my curve is concave up. Okay, so let's say it's something like this. All right. Does that look like the object is speeding up or slowing down? Speeding up, okay? In this case, we know the acceleration is positive. But what if I had something like this? Let's see here. I want negative. So, okay, so something like this. Does that look like it's speeding up or slowing down? So this is my position, and this is time, right? It's slowing down. However, it's still concave up, meaning that the acceleration is going to be positive there. So it's speeding up when it's like this, but slowing down when it's like this. And in both cases, the acceleration is positive. But what's different about both of these two curves?
One is concave up and one is concave down.
Well, they're both concave up, right? They're both like making a happy face.
One has a negative velocity.
One has got a positive velocity, one has a negative velocity. Here, the slope is positive. So we have a positive velocity. Whereas on that second graph, we have a negative velocity. So, if your position is positive here, if you've got one of these two graphs, you'll be speeding up if both the acceleration and the velocity are positive. However, if they have different signs, then you'll be slowing down. Now, these two cases I think are a little bit more obvious, but what gets confusing is when the acceleration is negative. So let's look at two other cases here. I'll kind of summarize it all in a second. So let's say you had a negative acceleration, meaning concave down. So acceleration is negative. Does it appear as though the object is speeding up or slowing down? What's going on with the velocity? Is it getting closer to zero or further away from zero? Slowing down, right? Okay. Slowing down when the acceleration is negative, but the velocity is positive. However, if the acceleration is negative, but the velocity is also negative, you're actually speeding up. Your speed here is being notated by the slope. And while it is going like the position is going down to 0, the speed is increasing. Or speed is the absolute value of velocity. Okay, the slope here, it's becoming more and more steep, I should say. Right? It's becoming more and more negative, but the speed is increasing, even if the velocity is decreasing. Okay, so let's try to sum up all these different cases here. Got too much going on here. Okay, so if the acceleration is positive, okay, that's when your position curve is going to be concave up. It's either going to look like this or like this, right? Both of these are acceleration is positive. But in one case, the velocity is negative, and in the other case, the velocity is positive. It's not a V. We could also consider when the acceleration is negative, in which case the curve of the position is going to be concave down. So either your graph is going to do something like this or something like this. And in one case, the velocity is positive, and in one case, the velocity is negative. The two cases in which the object is speeding up are these two cases. Whereas the other two cases, these two, you're slowing down. Okay? One way to think about it is the velocity getting closer to being 0, or is it moving away from 0? If it's getting closer to 0, the object's slowing down. If it's moving away from 0, positive or negative, it's going to be speeding up. Now, what might be an easy way to remember this? Like if you're looking at these signs, what do these two cases have in common? They're the same sign, right? So that's really what you want to be looking at. If the particle is speeding up, that means that both acceleration and velocity have the same sign. Whereas the object will be slowing down if the acceleration and the velocity have different signs. So we need to check both the velocity and the acceleration at t equals 1 to be able to make a conclusion here. So the actual calculus that we're going to be doing really isn't any different than what we've been doing. We're going to find derivatives and whatnot. But we're going to be looking at both velocity and acceleration to be able to answer this question. So let's go ahead and do that now. So velocity, which is the derivative of position. Okay, I'm just going to differentiate this, not integrate. So this is just the old school power rule. Yeah, it's going to be negative 3t squared plus 8t minus 7. And I'm going to evaluate that velocity at t equals 1. So negative 3 times 1 squared plus 8 times 1 minus 7. Negative 3 plus 8 would be 5, minus 7 is negative 2. Okay, so the velocity at time 1 is negative. That's not enough to really answer our question here, because it could be either one of these two cases. And to determine that, we need to look at the concavity of that position graph. And we're going to do that by looking at acceleration. So let's find the acceleration. The acceleration is the derivative of the velocity. So we're just going to differentiate that velocity function one more time. So negative 6t plus 8, that's it for acceleration. And if we want to find the acceleration at time equals 1, we're just going to substitute 1 into t. So the acceleration at time 1 is 2. All right, so let's see if you've been paying attention. Is the object speeding up or slowing down? So how do we know? So, yeah, the velocity is negative. The acceleration is positive. They have different signs. So what's our conclusion? Yes, slowing down. Very good. Okay, so the particle is slowing down at time is 1 because you can either say the acceleration and the velocity have different signs, or you can just say what their signs are, because the velocity at 1 is negative and the acceleration at 1 is positive. Ooh, that's a tough one. It's not as easy as you might think. You might think, oh, you just have to look at the acceleration. That'll tell you. But it's really the relationship between acceleration and velocity that'll tell you if you're speeding up or slowing down. And part of that reason is because the speed is the absolute value of velocity. All right. Any questions? All right. I just have a few more for you here. So anyone need a little bit more time to write that down? It's okay if you do. Okay. All right. Number 3 says a particle moves along the x-axis, and its position is given by that cubic function. Determine all values of t when the particle is at rest. Okay, so we've actually answered ones like this before. What has to be true for the particle to be at rest? What's 0? Position. Not necessarily position, because I could be at position. I could be moving through position 0, right? But what has to be 0? Your speed, or more specifically, your velocity. Although if one's 0, the other one's 0, because the absolute value is 0, 0. But yeah, basically your speed has to be 0. So it doesn't matter where I'm standing, right? I could be standing over here, but as long as I'm not moving, I'm at rest. So for the particle to be at rest, the velocity has to equal 0. Okay, so the velocity, which is the derivative of the position, is 3t squared minus 6t minus 45. And we're interested in where that is 0. So we could just set that equal to 0 and solve it. We've got a nice little quadratic here. And your quadratics, you want them set equal to 0 when you solve them anyway. And then you want to look for any GCS that you could potentially divide out. And in this case, we can divide out a 3. So if I divide both sides by 3, I'm going to get t squared minus 2t minus 15 equals 0. And now this factoring becomes a little bit easier. All right, what are my two factors here? Okay, good. So t plus 3 and t minus 5. So the two t values where this function equals 0 are negative 3 and 5. And so those are the two times when the particle is at rest, because at those two times, the velocity is 0. So the particle is at rest at t equals negative 3 and t equals 5 because the velocity at those times is 0. Or I'm just going to say v is 0. There we go. Any questions about number 3? That's kind of a throwback question. Yeah, we dealt with that last semester, but I feel like it couldn't hurt to bring it back. Okay, I think it's good to review like these relationships every once in a while, just so that you don't forget them. Okay, we've got one last question. It's a 3-parter, though, of course. A particle moves along the x-axis, and its position is given. Determine all intervals when the particle is moving to the right. Okay, what does it mean when I say moving to the right? How do I know when it's moving to the right or versus like to the left? The velocity has to be positive. So here the velocity has to be positive. If the velocity is negative, we're going to be assuming that the particle's moving in the negative direction, like towards negative infinity, which is to the left. So we need to solve this inequality rather than an equality. Let's see how we can do that. So first, let's find the velocity function. It is the derivative of the position function. So that'd be 3t squared minus 36t minus 39. And I'm interested in where this function is positive. Now, solving a quadratic inequality is very similar to solving an equation. You're still going to try to factor it, find the zeros, but then we'll find our solution set a little differently. So let's divide everything by 3 to simplify our quadratic here. Get 3 squared minus 12t minus 13. Okay, we still want to try to factor it so we can find the zeros. And the two factors here would be t plus 1 and t minus 13. But then you're going to stop here. And you're going to draw a number line with the two t values where this function equals 0. So the two t values are going to be at -1 and 13. This is our velocity graph. And we're not going to draw like a full-on graph of this, but what kind of graph are we expecting this to be?
This one shows positive and negative between the intervals.
Yeah, well, we could go a little bit, we could do a sign chart, yeah, but my question is like, what graph does a quadratic produce? It's a parabola, right? And is this going to be a parabola that opens up or opens down? I think it's going to be like a happy parabola or a sad parabola. How do you know? Yeah. Because, yeah, the leading coefficient's positive, so we know that parabola is opening up. So just like a regular parabola, like y equals x squared. And so if we know where these zeros are, we know that the general shape of this parabola is going to do something like this. Okay. Now, if you're a little uncomfortable with like making that little sketch, you can always fall back on just making a sign chart and picking representatives and do like the plus minus thing. But I think with quadratics, sometimes it can be faster to just think of it like this. Because we can see right away where the velocity is going to be positive. In other words, like where is it above the x-axis, here and here, and where is it below the x-axis, which would be down here. We're interested in where it's above the x-axis, where the velocity is positive. So there are two intervals. We'll just list them both here. Okay, the particle moves to the right when t is an element of this set. In other words, when t is all the values between negative infinity and -1, and also between 13 and infinity. You could also use inequality symbols and just say like t is less than -1 and t is greater than 13. That's fine too. But I'm going to use this set notation. This is a little lowercase epsilon symbol, by the way. Okay. It's almost like a little e, sort of. All right, part B says determine all intervals when the acceleration is negative. Okay, so the acceleration is going to be negative. We've got to find what the acceleration is first. The acceleration is the derivative of velocity. So the derivative of 3t squared minus 36t minus 39 is going to be 6t minus 36. Now this inequality is going to be a lot easier to solve because it's linear. So you just solve it using your properties of equality. Right, adding something to both sides, that sort of thing. So yeah, we want to know, when is the acceleration negative? So we're looking for where a is negative. 6t minus 36, when is that negative? Okay, so adding 36 to both sides and dividing by 6 is going to give us t is less than 6. Okay, so the particle has a negative acceleration when t is less than 6. Any questions about that one? Okay, our final question. It's not going to take a whole lot of work. It's going to take a little bit of thought. Okay, so get ready for this one. It says determine all intervals for where the speed of the particle is increasing. In other words, speeding up. Now, we talked about this on the front page. How do you know when a particle is speeding up? When the signs are the same. So we're looking for intervals where either the velocity is positive and the acceleration is positive. So that's got to be one case. Or when both the velocity and the acceleration are negative. So I think the easiest way to kind of put this together, we've already done all the work to see when velocity and acceleration is positive or negative, is to look for those intervals that overlap. So here's the velocity sign chart between -1 and 13. Okay, it's going to go positive, negative, positive. And the acceleration sign chart only changes at 6. Okay, it's got a negative acceleration before 6 and a positive acceleration after 6. So we're looking for where the signs are the same. So that's going to be between -1 and 6. They're both negative. And after 13, they're both positive. So the two sets are going to be between -1 and 6 and 13 and infinity. All right, I know we're right up against the bell here. I apologize for that. But let me go ahead and give you your homework.